The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone. Welcome to today's session on unlocking the power of geospatial artificial intelligence for humanitarian use cases. My name is Rohini Swaminathan. I currently work with the Climate and Environment Data Unit at UNICEF. It's an absolute pleasure and honor for me to introduce this new episode in the GeoAI Discovery Series. So we launched this series back in 2022, and we discussed diverse topics from GeoAI applications and policies, ethics. We also had thematic sessions on climate actions, spatial digital twins, energy, ecology, agriculture, water. And more recently, we have been focusing on geospatial large language models, as well as GeoAI and education under the leadership of the curator of this series, Maria Bravelli and Andrea Manera. In case you have missed any of the episodes, don't worry at all. You can watch the recordings of these events on YouTube or on the neural network to which you're connected right now. Without further ado, I will introduce the speakers of today's session. First, we have Rami Aluthwa, a senior solutions engineer at Esri, specializing in geospatial systems. With a bachelor's degree in landscape architecture, he focuses on GeoAI, automation, and architecting geospatial systems. Rami works closely with many nonprofit organizations, especially many UN agencies, and his expertise includes desktop, imagery workflows, GeoAI capabilities, and field data collection, establishing him as a recognized expert in architecting robust enterprise geospatial systems. Welcome to the session, Rami. We also have Lisa Town is an earth scientist specializing in remote sensing for earth and environmental science. She joined Esri in 2023 as a solutions engineer as well for the National Government Health and Science team. She is also a science advisor and mentor for the NASA Develop program, and Lisa holds a master's in marine geoscience and a bachelor's in geology. To introduce today's session to all of us, I would like to invite Dr. Michael Gold, a good friend and a professor of GIS at University YUM in Spain, and also a global education manager at Esri, who collaborates with a lot of Esri offices around the world and with other international organizations on capacity development projects. Michael, the floor is all yours. We are quite excited about today's session and to learn more from you.
Thanks a lot, Rohini. And it's a pleasure for us to be taking part in this series. We've been watching the AI for Good series over the years, and speaking with the organizers, with Andrea Manara and Professor Maria Brovelli, we're very happy to be able to bring our sort of story to the series. And that story is integrating GeoAI into GIS workflows. So being able to maintain a GIS workflow and utilize the power of GeoAI when and where necessary. So we'll show you some excellent real-world case studies from the humanitarian field. And without further ado, I would like to turn the microphone over to my colleague Rami, and then later to Lisa, because we've got a lot of content to look at, and then we're looking forward to your questions now live, and also please contact us if you're watching this on video. Thanks. Rami.
Thank you, Mike. And hello all, I'm gonna share my screen. And thank you all for the opportunity today to present to you AI in the AI for Good workshop on the different GeoAI workflows in the humanitarian. So today we're gonna be going through I'm having some issues, by the way, sorry. Some Zoom issues on the other side. But I'll keep going and assuming I'll have no interruption with this. So today we're gonna be covering some GeoAI for humanitarian relief topics. We're gonna cover a little bit of GeoAI, a brief capability of GeoAI, an overview. We're gonna go through different ready-to-use deep learning model. We've all been hearing about all the different deep learning models available for end users, and we're gonna have a brief cover on that. We're gonna also cover some foundational models and discuss training your own models and creating models that can help you through your humanitarian work around the planet. We're gonna touch base on integrating segment anything model, SAM, as we all know it and might have heard of it. And then we're gonna talk a little bit about prediction with machine learning and touch base on the latest with GenAI and how can it help us within our different workflows. So to start with, let's have a brief overview on GeoAI capability. So we're gonna be tackling different elements within GeoAI, but I'd always like to start with the main topic that GeoAI doesn't sit alone. We never do GeoAI just because it's interesting and let's do GeoAI. We do GeoAI to help us in a certain workflow. It's a mean to an end, to save us time, to fasten our workflow processes and whatnot. And that doesn't come alone. It comes with other capabilities that we need to work with as different visualization and exploration workflows, as different spatial analysis tools that might be available for us in a GIS field to work with. And all of these together combine in a workflow. So in today's presentation, you're gonna see us going through a lot of GeoAI workflow, but always keep in mind that that's not possible without the other workflows. Not any deep learning workflow that we can go with will take results and use it out of the box. We most of the time have to do some QA, QC and work with different tools to really automate the cleaning of our analysis. And hopefully within the flow of the presentation today, we'll get an idea of that. So in a geospatial context, AI really helps us see things that we can't see or make seeing things faster in an image or in a text to help us learn different new workflows, teach models new different workflows that we work with. And we're gonna see a lot of these touching on different aspects of data types that we might work with. It helps fasten our reading capabilities, analysis, and creation of different analysis and layers. Within these topics, we really can focus on multiple subtopics that can come under and be supported with different tools and different capabilities within the AI sector. We're certainly going to see some segment anything today, but it's not alone. We might work with unit, we might work with mascar CNNs, with different ways to really capture and see things through our imagery, or using multi-dimensional models to analyze data, or random tree models, for instance. So there's a lot that can happen within these lines. And to have an idea what we can work with from an extraction workflow, and we're going to dive deeper into this as we go. We can do different object detection workflows, or we can extract text from or locations from different text as location entities. We can classify text with different LLM models, and we're going to see that later on. So it helps us under different sectors, and this is just a taste of what it can do for us within a GIS workflow. So to focus on AI, I always like to start on, or GeoAI particularly, to start with the bigger concepts and dive down, because this is all a build-up. And this came over the past 5-6 years as we're building and experimenting with different workflows. We start with AI, and that started to be common when we started seeing different workflows where the machine is taking decisions, where the machine is saying, if this goes like this, do that. And the moment it starts picking that up, it's an overarching approach where under it we'll have different sectors of machine learning, deep learning, LLMs, and GPTs. To jump to machine learning, for instance, we're going to see examples of different regression models, different statistical models that the machine can apply on our input data for an output analysis that we're looking for. Then we go to deep learning, where we utilize neural networks to make more complex workflows, as, for instance, feature extraction from imagery. And lately, we've been including LLM models, which we can extract different entities, different features from our text to GPT assistant, where we ask the GPT something and it's prompted to return certain replies based on how we program it or design it. And as we go, we're gonna exploring this more and more. Now, an AI for GIS workflow, it really focuses on two different verticals: GeoAI workflows and AI assistants and AI agents. And we're gonna be exploring both of them and utilizing different agents to work with different data and seeing different GeoAI workflows that fall under vector, tabular, or imagery workflows. From an AI machine learning and deep learning workflow, I'd like to focus that GeoAI within the GIS system, it's more an open source library that is built and compiled all together to do the variety of different workflows that we can see on the screen. And again, this is just a touch base on, for instance, damage assessment workflows or forecasting workflows, where we're going to see later a GEnAI data example for forecasting above ground biomass, or working with text, and we're seeing later a WMO example on really extracting information from our text. So all of these models can come together to enable a GeoAI workflows. It's based a lot on new available models that are out of the box that we're going to see through the Living Atlas, how we can get access to them and download them. But it's also built on foundational models, which we're going to explore and talk a little bit about training these models and working with them. To start with the libraries, we make available the different out-of-the-box deep learning libraries through the GitHub repo, and we'll share these later at the end of this workflow through a QR code where you get access to all of these different resources. So these libraries are built on top of the very famous open libraries that you might be working with, as PyTorch, as TensorFlow, as Matplot, for instance, and they enable us for different workflows, where we can go through open Python libraries, access these tools, and work with them through any taste of our interpreters, whether it's VS Code or your notebook of choice, where you can explore different foundational models that are accessible for you to train, for instance, faster RCNN or mask RCNN or UNet and whatnot. So these workflows, it's good to understand that it's not only imagery or it's not only text, it's an overarching concept built on top of these libraries. So an end-to-end GeoAI system, and that's something that we're always going to keep in mind. Whenever we're talking about a GIS workflow, or whenever we're talking about a deep learning GIS workflow, where we utilize these open libraries, the workflow really spans over a couple of different steps. And we're going to explore more or less most of these steps, where we start with data access. We need an input to our data. This data could be a service. This data could be provided through a JSON output through an API, or could be a CSV repo, or could be any form of data that is living within your systems or on the cloud. We're going to explore different data prep workflows, where we need to really clean the data, get it ready for our GeoAI workflow. Then the most essential step, I guess, is if we're ever going to train a model and we're not using out-of-the-box models, and we're going to see that different tastes of both, it starts with really picking good data labeling. And you all know how challenging that might be to creating good, complete data sets that really conveys what's happening in the real field. Then we move to different model training, and that model training can vary depending on what workflow we're going to use. What foundational model are we going to use? Is it a pixel classification or an object detection, for instance? And finally, how we take these models, inference, and get the results out through deploying them locally or on production and scale. how we can make them consumable, available for the different end users, and certainly create products on top of these AI-driven data sets to really understand what's going on. For instance, understanding that damage detection, we need to disseminate the data that is inferenced, and for that, we'll see different solutions that can take us through that. So when it comes to deep learning, there's two different workflows that I'd always want to keep in mind whenever I work with deep learning. And that will fit the slide before as the workflow from training, labeling, training, and inferencing. Sometimes I might want to skip training and labeling, and I just want to use a pre-trained model if it works for my use case. And in some use cases, I might find out that I need to fine-tune a model or create a new model, follow a reinforcement workflow. And that can take me through other section of training my own deep learning models. We're going to start with pre-trained models because usually they're the cheapest. Most of us might have challenge getting access to GPUs. We know that deep learning is a very high demanding, compute demanding workflow, and we might need access to GPU in order to train these models. And if we can skip that step, that would save us time and would save us a lot of other time on labeling the data. So to do that, we can use different pre-trained models that are available. And they help us, as I said, imagery requirements for model training are eliminated. We don't need to work with training data. We don't need to label data, and we don't need to train AI models. So we avoid the massive compute requirements. These pre-trained models are available out of the box and within the Living Atlas. And I'm going to show a fast demo on that and jump from this slide in a second. But what I'd like to highlight here is that there's now something around 75 plus available deep learning models to utilize from the Living Atlas. And these models are growing. So every other short period of time, sometimes months, sometimes weeks, we're introducing new models. We're updating the existing models so they perform better. So they're always retrained. There's always new capabilities added to these models. And for that, let's jump on a fast tour where we're going to go to the livingatlas.org.js.com and search for DLPK. So DLPK stands for Deep Learning Package, and in fancy words, it's a zip file that collects all of these data or models and open functions that you can utilize for the deep learning workflow. These models, as you can see, span over different workflows. They can be either building footprint extraction, they can be land cover models, they can be different high-resolution land cover, LiDAR models, tree segmentation. There's plenty of them, and I'm not going to go through each and every one of them, but I really invite you to take a step there and see how these models work and if they fit their use case that you're working with, because this is always, as a reminder, cheaper than training a model and going through that workflow. Jumping back to my presentation. So when we work with these deep learning models, we can get different results out there. And something that I really want to highlight is when I started to mention that we want to do extra analysis on the data, extra QA, QC steps, quality assurance, and quality control. What we want to do there is make sure we automate our deep learning, understand how it works, and use the different libraries to go through multiple workflows to inference a data set. So what I mean here is, imagine you're working with an image and you want to extract buildings out of this image. Sometimes the model sees the buildings at different scales, depending on what you specify as a tile size. And the boxes we're seeing on the screen are different tile sizes. So you define that the model should look at a smaller tile size, a medium tile size, or a bigger tile size. And the building size changes there because we see bigger buildings in here don't fit within my yellow boxes. So they need the more blue one. And that's where we really want to push these out of the box models. If I run a model and it doesn't give me good results on one scale, maybe I want to try another scale. Maybe I want to go on a different cell size. I got 20 centimeter imagery. Maybe I want to go on 50. It's too fine for that workflow. So keeping these concepts in mind is very critical as we're going to get through further workflows and understand what are these deep learning models. So the first example I want to show here, and this is will come to the later use case that we're going to demo on detecting informal settlements. What we started with is a concept that we thought if we're done multi-resolution, imagery is going to get better, or the model is going to get better results. If we look at the image on this side, this is a use case we worked on in Catalonia, where we were just testing with extracting building footprints. And we noticed that if we run building footprints on 30, 40, or 50 centimeter, we're going to get different results. If we compile these results, we're going to get a more complete picture. And for that, we actually scripted a tool that can work on multiple imageries, and we'll make it available later in the reference document that we're going to share. So that will help us get a full image, and we'll understand this as we're going to use the tool in our informal settlements mapping, because informal settlements can be very challenging, and keep that idea in mind that they're small and tiny sometimes. So, and close to each other as features. So the more resolutions I might work, the better results I'll get in there. So with that, I want to actually jump to this demonstration. And I'll look into here. And what we're working on is a very important use case that we've worked with for flying labs, South Africa flying labs, where they were trying to detect informal settlements to really know the size of people that might be at risk of flooding of the stream that is going here. And we thought that the multi-resolution workflow that we just explored can help us drive these different settlements. And for that, the tool that we're going to work with is available in here. And again, I'm going to share the link for it as it's publicly available within our ArcGIS online, and you should be able to download it. So keep an eye for this one in the document later on. If we download the tool and open it, I've got it loaded already in here. What I'm doing is I'm importing an imagery of Alexandria image. And this is an image captured, as I mentioned, with South Africa flying labs. It's drone imagery, and it's actually 2 centimeter imagery, which might be a little bit high resolution for this workflow. So we got the imagery in, and as I mentioned, we wanted to work with different cell sizes. So I specified the cell size of 0.05, 0.1, 15, and 20 centimeters. Now, what the model will do is inference at each scale and detect any objects that are in that image. In this use case, I text prompted it for 10 gray rooftops, shelter houses, and building structures. Now, note that I'm using TextSAM feature extraction workflow, which is the out-of-the-box model that is available to us through the Living Atlas that you can just access in there. And let's see, Sam. So we're using actually this model that if I click, I can go and download the model out and make it available and accessible. So download that guy, reference the model definition sitting on my own machine, and then running on this size. Now, as this model ran, there's a very detailed QA/QC in the back end where it's running different resolutions, cleaning the data, picking the buildings from each resolution, and spitting one feature. So the idea that we're looking at here is we're able to really extract with very high accuracy our buildings and get an accurate estimation to a certain extent on these that are at this side of the river, where there might be a risk of any flood whenever the water level rises out there. Now, that doesn't stop there. With different deep learning workflows, there's also classification workflows that we're gonna dive into in later, but to mention that there's the classify pixels using deep learning where we can input the same imagery, and this is very critical as we've got the same imagery through different workflows, got the imagery in, and this time I've used another model, which is high resolution land cover. And we actually showed that earlier on in the Living Atlas, some input parameters, and there's also in the resources, more details on what is batch size, what is padding. And we're gonna talk about these parameters, and you'll see me mentioning them as we go through. So we put this in, and then we were able to really classify a land cover that covers all of these different topics out of the box. Now, notice that the land cover here doesn't have the buildings, we removed that and we got it through a different deep learning workflow, the one we just showed before. And that's how combining different out-of-the-box models can really get us to a place where we automate a lot of the extraction and know really where are things happening, where's our water, which also was driven from the land cover classification action. So some workflows to keep in mind. Also, this can extend a little bit further to extract trees through the same workflow, where rather than doing a text prompt and the multi-resolution on thin gray, we can just go change this to tree. And then if we run this guy, we should be able on this use case to get exactly a similar output. And to compare this to our imagery, to have an idea how our trees look like, we can zoom in a little bit and we can see that most of the smaller sized trees that are this size are detected. Now, there's something very important to mention, is that not every single tree will be detected, because at the end of the day, deep learning will never be 100% accuracy. And if we look closer, we might see that 1-2 trees are missed here. So we always want to go over the data. We might get our models from 80 to 90% accuracy, but there's always going to be that need to clean the data and make sure it looks better. Gonna head back to my presentation. So we've seen till now a little bit of out-of-the-box models, a glance of what they can do for us. But there might be some use cases, as we're gonna get to later, where we don't have a model that can do the work that we want to work with. It's either not good enough or it doesn't exist. And for that, we might want to explore some of the foundational models that are available to train for our workflow. Now we're looking now into training your own model, and keep in mind that now we need to get into labeling and data prep, which is a very critical step, or both of them are very critical steps in here, as the integrity of the labels and how complete is the data will really skew how the model works and define how the model influences the data later on. So with foundational models, what we can do is get a bunch of different foundational models that can be available for text workflows or image or speech or imagery or 3D and LiDAR data. Depending on the workflow that we're working with, take these foundational models that are trained on massive data sets and rework them, apply reinforcement learning on them on specific use cases, on specific features, to get a fine-tuned model that we can work with on our use case. Now, there's plenty of out-of-the-box available foundational models for you to train, and we really want to understand what are these models. There's models that support, for instance, as I said, UNET, or mask RCNNs, or single-shot detectors, or SAMLoRA models that have been lately added, and we're going to see that in a moment. These models are very critical to understand what workflow I'm going to work with, and accordingly pick the model to apply it on my own use case. And we're looking at different use cases here where I'd like to highlight some. For instance, this is some work that we've done with Halo, Trust, and Mariupol to really estimate the damage that has been done. And this was done through a UNET workflow around 3 years ago, where SAMLoRA didn't exist. And I really picked this one specifically because as we jump to this damage detection, we needed in here. So this guy is in Grenada, and Lisa's going to show us that to us in a bit. This took something around 30 to 40 training samples and around an hour or two of work, where this guy took around 10,000 training samples and a couple of days to a month of work. And it's really critical to know what model I want to use, what results I'm looking for in order to move forward with the deep learning workflows. And a lot of time we spend excess amount of times training a mask RCNN model where a deep lab model could have been better for my workflow, or a faster RCNN model. So understanding the architecture, how these models operate, is very critical, and also on which neural networks I want to train them. Do I want to build a, for instance, if I'm using SAMLoRA, we're going to see vision transformers, huge, large, and basic. Do I want to start testing with smaller models and move to my huge models? Or do I want to test directly with my huge models because I know the use case and I've tried it before? So really knowing which backbone models is very critical in here. And one thing that I really want to show is, if I look into model architecture, this is another resource that will be shared in the document. There's deep learning model architecture documentation where we can get a brief idea of each of these models. What does it do? We can go deeper into it and understand each one of them, but then we understand what type of workflow. Is it pixel classification, or is it an object detection workflow? Or is it a feature extraction or image translation? So really knowing what I'm looking for, how fast I want it, and how accurate I want it dictates which one of these different models we can use. So, as I mentioned, there's the Halo Trust example, and I particularly picked that image knowing that we will get to this part. We worked on this around, as I mentioned, 2 years ago, and I want to take you through a series of use cases where we've come to the Mariupol example, but our work with Halo and how it started with these masked RCNN models. So for that, let's jump to my story map and let's explore this story. So originally, back in 2022, Halo reached out to us with a simple use case. We are working in a demining sector. We're working with different countries around the planet, and we'd like to detect the change to the landscape after we do a demining workflow. We want to know which areas are being utilized for agriculture, which areas are being built, and where are people going back to the lands that were cleared. So originally, they collected that data on field with such documents. They got in, and we got into a Sri Lanka example. So we're looking at Sri Lanka satellite imagery acquired by Halo from Planet, and this was 50 centimeter image, which is the most common imagery that we see that's being used across the humanitarian sector due to the availability of it. So in the imagery, they were looking to first detect buildings because they cleared a lot of mines in this region, and they want to know where are these buildings. We started with what I showed you earlier on, the building footprint extraction. The sign as this is the Halo story, so loading this. So we got to the building footprint extraction, and we wanted to start with the Africa model. Now remember that there's different models for different areas, and as the geography change, the performance of the model will change. This model, the Africa model, is trained in Ethiopia, which got a lot of added empty lands that might be similar or to the north of Sri Lanka, plus the building materials might be similar. Now, it's not the same, but it's much closer than using a building that is trained in Europe, for instance. So keeping that in mind, we downloaded the model, we did some tests, and we actually saw that we're getting 63% accuracy when using the out-of-the-box model. I'm signed into different places, so it's me through that. Let's go back up here. Perfect. So now it's loaded. So we tested that model, and we've got the 63% accuracy. As we can see, these greens are actually buildings that we've detected, and we can see these in, but the reds are false positives out there, which was a little bit triggering. There's no building here. There's no building here, for instance. And we wanted to get better results. So to do that, we thought, let's retrain the Africa model and take a reinforcement learning workflow. We labeled around 2.7 training data sets, and we make sure that we captured all the different training samples within this area. Now look at this number and keep an eye for what Lisa's gonna come up with later. After we got this, we trained the model, and we actually inferenced this area. And this time we got almost, so this is per zone. The total count of buildings was 74,000 for all of our region. And we've got pretty good accuracy here. So as we zoom to a random area, these are different zones that they're looking for. We're seeing that we've got way more structured data, and the model accuracy was actually improved to around 82, 83% with 2,000 training data sets. Now, that workflow worked good. They wanted to test it in a different cleared zone, and that's a neighborhood in Afghanistan, where they actually also got this data out. and inferenced with the same model that we trained in Sri Lanka, and again, got some, well, we retrained the model, but now with less data, sorry for that one, which was 1.1 thousand or 1,100 training data sets. And then we inferenced on the other side where we got all of the buildings, well, all, let's say around 90% in this use case of the buildings that are out there in their area of interest. And keep in mind that they're interested in the zones. So actually with further geospatial tools, you can utilize different, in this case, JavaScript arcade language to really sum every single building within this zone. And we've known that in this zone, there's 140 buildings that are constructed in a clear zone that Halo cleared. So it's very critical to look at these data sets as they help Halo in their workflows. And then as they went through this, the war started, and they wanted to size the damage in order to know where might there be unexploded ordnance. So we worked with the Mariupol data, and we actually had to get something around 60,000 buildings or 64,000 buildings in this use case, which were open street maps buildings that we got in. We labeled 3,600 out of these buildings, and we used 6,000 other non-damaged buildings for our training data set, which spanned around all these different areas. So we took smaller AOIs around the red areas and trained the model on damaged and non-damaged areas. When that was done, we were able to size the damage more and really get a much better view of the damage that happened in Ukraine. Then we tested in Kharkiv on a different landscape and noticed different imagery. We noticed that the accuracy dropped, and it didn't drop that much because we were still capable of capturing some of the damaged buildings. Now we're missing some, which is telling us we might need to repeat the same workflow. The challenge here, the imagery wasn't as good, and that is very crucial because if I compare both, you can see that this is much clearer imagery in here. I'm going to zoom to one of the areas. That's my building, and you can see the imagery is a bit clearer compared to what I have in here, and that really dictated how the model operates. So with that, we've seen one use case from the Halo Trust, and I'd like now to move to the more decent addition of the open models that are available. And this use case, I want to focus on the segment anything model, because main challenge that came from the workflow before is the amount and size of training data. And you've been seeing that. We've got thousands of training data sets that consumed high or large amount of time to digitize and to create. So we wanted to work with a better, faster workflow. And to build that workflow, let's start with the segment anything model, the model that came around 2 years ago from Meta, where we integrated that model into the GIS system, where the model is literally working on images that you input, and it's been trained on millions of images with different vision transformers. It's prompted with different labels to segment different features and look at everything within the image and segment. So if you run something with for instance, this image with segment anything model, it might segment the scissors, or it might segment both circles or one circle, which is really a challenge. Plus, it's going to look on all the image. Now, this is pretty good if we're working with a use case that we have no labels, nothing, and we just want to segment everything in there. But in a lot of use cases, we're looking for something specific. And for that, TextSAM came in. Now, when I say TextSAM, think of the building detection and tree detection in the informal settlements, where we actually used this guy to detect specific features. And how this TextSAM work is really combining segment anything model with the grounding Dino open source model together. TextSAM is pretty good at segmenting all features. Grounding Dino is good at picking features. If you say the object is tree, any feature that overlaps a tree will pick it up. This was pretty good, and you saw that it did a great workflow with the building detection. Yet, it's still doing a full segmentation of the image, which might be time consuming. It might be very fast sometimes if you're working with smaller imagery sizes, you just want to put a text prompt, it's a great use case. But if you're running at scale, you might want to make that a little bit faster and segment faster specific objects. And that was made available with segment anything model low-ranking adaptation, or SAMLoRA as we're going to refer to it. And SAMLoRA is a combination of SAM and the low-ranking adaptation model, where we freeze SAM on a specific training data set, and we tell it just train on this exact features: buildings, trees, damaged buildings, undamaged buildings. The great thing about the model is that it trains really fast. It takes very minimal training data sets, and you might get away with 20, sometimes 30 features in creating a model that does the workflow for you. So imagine we were working with a month of work around 2 years ago, and then as these models are getting better and faster, we can now do similar workflows in, I'd say, 1-2 hours, depending on what is the workflow. Now, we're making this sound easy and nice, which is reality if you get an understanding of how these models operate in the backend. These models can be affected by any tiny change, and you really need to understand the imagery. I got the opportunity before to talk about resolution, and I'm going to mention resolution again. I really like this screen capture because we're technically looking at both images that are exactly the same, but actually one of them is 0.1 and one of them is 0.2 centimeter. The number doesn't really show here. But I know that if I change the resolution, the number of columns will change. You might not see that in your own eyes, but if you zoom in enough, you'll see that the pixel sizes are changing. And if the pixel sizes are changing, the model will see different images, because the model will always look at a specified tile size. We know 256, 512 pixels. These are the most common. So it's going to look at 500 by 500 pixels or 512 by 512 pixels. If you multiply that by 1 centimeter pixel, we're looking at 5 meters. If you multiply that by 2 centimeters, we're looking at 10. So doing that math and understanding the size of feature, what tile size you're going to use in combination with the cell size, can easily get features that we look at here. We inference at 1 centimeter, and you see we're barely getting these small settlements. We inference at 15 centimeter, and we're only missing this one because it's a little bit bigger than the 15 and it's not fitting exactly in the chip. So keeping that in mind, knowing the text prompt, are you looking for one feature? Are you looking for the same feature? And you can have river and streams, for instance, because they're the same, or buildings and rooftops, etc. Knowing what text prompt we're going to use will dictate how the model operates. Then going to training data, we're going to also see that later in the hurricane example, but this is very critical, even in this example. To get buildings, if we want to train a model, we really want to capture everything in there. So we want to make sure that our data is inclusive and we don't train on data sets that aren't labeled. So our training data and our masks matter. Our batch sizes matter. What GPU are you working with? What is the machine you're working with? Will dictate how fast you can go through the workflow and how many images you can process at a time. Then going back to the foundational models, if you're training a model, what foundational model are you using? Do you understand that the unit will do pixel classification, or I want to do an object detection? For this use case, we're showing SAMLoRA, so it's mainly pixel classification, where unit is also pixel, but they operate differently because we've seen that one might take 2,000 features of training data and the other might take 50 to 100. Now, another very critical step if you're going through a feature classification workflow, and in this use case with the SAMLoRA model, is taking these training data sets and visually inspecting them before moving to a training workflow. Because sometimes training might take 5 minutes and you can afford losing that time. Sometimes it might take 2-3 hours and you don't want to lose that time. I'm not going to say more with SAMLoRA because usually it trains within that time frame. So once you train that, once you export that training data, you want to visually inspect it, see that all the buildings are labeled, in this use case also all the roads labeled, how many features do I have in each chip? Does it sound reasonable? 9 to 10 features in here, a little bit more. What is my minimum and maximum? So understanding all of these, how many images do I have in my training data set? For instance, in a mask RCNN, you might need 1,000 plus images, while in here, you don't want to cross 500 maybe. but you can get away with 50, 75, or 100 training data sets or images in this use case. Now, once that is done, you also want to inspect after training the model, how did the model learn? Did you reach convergence at one point between your training and focal loss? How does your ground truth versus prediction look like? Do these look promising? Do we have accepted accuracy rate? If that's the case, then we go to inferencing. If not, we might want to review that. Another very critical element which we mentioned is the QA/QC. So you've seen the final output of the buildings, but you can see that there's a more fuzzy intersected input in here, which what the model got out. But with the right QA/QC tools, with the right workflow, you can clean this data and get an acceptable output out there. So how you can do that? You can utilize Python libraries, you can utilize different model builder workflows or out-of-the-box tools. One thing I'd like to share, which is also will be in the document, is, let me jump in here. Just a second on this. So the tools that I'm showing are actually available in the GitHub repo, and you will have that reference to the document. You might want to look for multi-resolution DL, and that's the tool we've seen already and how it works with the different parameters if you're a programmer out there, or post deep learning workflows to clean raster data, which is another QA/QC that is available publicly within this repo. Now, if you master these different tips and tricks, and you know what you want to utilize within the workflow, what deep learning model, what foundational model, what parameters out there, you might be able to apply the workflow on all of these different use cases. And I'm going to pick some, for instance, where we're able to size how many or the damage of fire on different landscapes. And the red here is area of forest that was damaged by fire. So you can actually classify that. Or train a SAMLoRA floods model, which actually took us on Sentinel imagery something around 20 minutes and 25 training samples of water flood, and it detected all of this over 2 Sentinel scenes. Or working with the damage detection we're gonna see, or trees and whatnot. So really understanding what model we're gonna use will dictate how it works. Now with that, we're gonna jump to a different demonstration. Lisa, who's going to take us through the Hurricane Beryl story and its devastating effects on Grenada. Thanks, Lisa.
Hello, hello. Rami, I'll take the screen from you if you could stop sharing.
Please.
All right, today we'll be walking through a quick and efficient method for assessing building damage using deep learning. Early this year, in July of 2024, Hurricane Beryl caused significant damage on the islands of Carriacou and Petite Martinique, leaving over 95% of homes either damaged or destroyed. So what we're looking at right now is we'll be working with a 1 meter resolution image from Maxar. This was taken on July 2nd, 2024. And to start our workflow, we will begin by outlining training image in our training data in our image. So zooming into the image first, we'll notice there are the intact rectangular buildings, while there are buildings that are damaged, missing pieces of their roofs. And we'll begin by outlining which buildings are damaged or intact by creating training data. Creating training data is very tedious, though. It takes a lot of time and manual labor. So what we'll do is we'll only zoom into one area of our study. And with the SAMLoRA model, we can pick an area of interest, save it as a bookmark for training, and then we'll only train about 40 to 45 features in total, and that only 40 to 45 features are needed. Here we have our damaged buildings in red versus our intact buildings in green. And if we bring up our attribute table, we do have the damaged as classified as 1, and then the intact classified as 2 in our attributes, so that the model can learn how to train what buildings are damaged versus intact. Once we have our training data, we'll export our training data for deep learning. With our input raster, we'll make sure that we have our Maxar imagery in there. For exporting our training data, we'll have an output folder. We'll bring in our polygons shown on the screen for our training data, ensuring that we're selected our class so that it can differentiate the intact versus damaged buildings. And then it's important for the SAMLoRA model to ensure that we have classified titles for our metadata, because that is what SAMLoRA takes. And then environments for our extent, bringing in our current bookmark extent that we're showing here. And for cell size, we do want to make sure that it matches our Maxar imagery. This does take a few minutes, so we ran this off screen. And moving on to our second step, we'll be training our deep learning model. What was output from the first tool, we'll be inputting as the training data for this tool. And for our model type, we'll ensure that we'll select SAMLoRA for pixel classification. Like Rami mentioned earlier, SAMLoRA is powered by Meta AI's Segment Anything model, which requires no additional training beyond the 40 features that we have in our bookmark showing on the screen. And then for our backbone model, we're choosing VIT-H for huge neural networks. And this does take, depending on your machine, either like 10 minutes to 40 minutes to run. So we did run this off screen as well. And then, for our training data too, just to give you a look of what the model is going through, it's blacking out or putting no values to anything else that isn't part of our training data, and the model is learning from there. And that comes to our last tool, which is to classify the pixels using deep learning. And we're bringing in our input raster, bringing in the model that we exported with the second tool. And then for our environments, also ensuring our processing extent and cell size match our imagery. And with that, we'll bring in our results, which shows the buildings that are damaged versus intact. We do have to do a little bit of cleanup. So in post-processing, we can cut out any areas that, say, are in the ocean. And with post-processing, we are cleaning up these areas. But not only that, we can also run some tools to regularize the building shapes and ensure that we have our buildings classified. And then navigating to our results. This is a reviewer for how we can look into accuracy as well as ground truth and predictions. And as we increase the epochs in our training, we do have increasing accuracy. And then going through our model metrics. In total, we achieved over 91% of accuracy and ended up with strong precision, recall, and F1 scores. So in the future, we can use the same model that we trained using that second tool on a different image, Maxar. And we can also create a dashboard. Let's see. So we can use the same model that we use on a different area, and we can also open these results, say, in a field application where field workers may use this map, and it's important to understand where to allocate resources. This is a public dashboard that we can also create, showing the contrast between the damaged versus intact buildings, which unfortunately is looking bleak in Petite Martinique. And of course, what's the most important about these scenarios is ensuring that we're bringing in the voice of the community and listening to their needs. We might be able to try to map out what is damaged by AI, but we really want to ensure that we have community input. So community members can bring in their contact information, bringing in their address, bringing in information about whether what damage has occurred and photos. So this can help allocate resources best to the folks who need it the most. And in conclusion, we have walked through how we can assess building damage with deep learning quickly and efficiently. Back to you, Rami.
Rami, can I ask you both a question regarding timing? I'm sure there are people listening wondering, okay, you say something takes 10 minutes or it takes a long time to label things. Can you give us an idea about sort of how long would it take for one of these workflows?
This is great question, Mike, and thanks for asking that. So as we re-emphasized, it really depends on what foundational model are you using. You would always want to get into the deep learning model package and access the EMD file, which I can reiterate where is it found in a bit, and check the accuracy if you're training the model yourself. If the model is available from the Living Atlas, usually the accuracy is reported there. Now, once I check the accuracy, is it good? Is it not? What is the backbone model that I want to use? And what is trained on? If the backbone model is mask RCNN, that's going to come to the question. It takes a little bit more time. It needs more labels, which means more training data. And then we're talking days, weeks. If we're talking, for instance, SAMLoRA or DeepLab, these are much easier and faster to train models. They're also more advanced. They came later in time. Now, these can take couple of hours or sometimes couple of minutes, depending on the model itself and what I'm looking for. If you notice in the damage detection that Lisa showed, we're detecting the damage, but we're not getting the accurate footprint of the building. And maybe that's not the case, because in such a case, you just want to know where is the damage and act accordingly. You want to size it. If you're a mapping agency, you might want to work with the mask RCNN, which brings exact footprints of the building, or a unit, for instance, depending on which model. And that might take, again, more time. So depending on the use case, I'll go and figure out what model I want to use, and that will dictate how long will it take.
And you're normally assuming it's on a big, kind of a beefy laptop, right? So you're not using big clusters or anything like that.
Yes. So most of the time you'll get away with a beefy laptop with good GPU on your laptop. There's some use cases with SAMLoRA where you actually might get away with a 4 GB RAM in a couple of hours, but that's smaller areas. That's smaller extents. You're not scaling on a size of a city. You're working maybe on a size of a neighborhood. That you might get away with a small laptop. Though you want to always keep in mind that if you're using a Windows machine, and maybe this is an opportunity to jump back to my screen to re-emphasize on this. So if you're using a Windows machine, you can open a command prompt. I don't have any deep learning libraries running or deep learning workflows running at the moment, but there's a very handy command that I'd always keep in mind, which is NVIDIA SMI space -L, and I use 5 to make it print every 5 seconds. This will first tell you what is the GPU you're working on with and how much are you utilizing of the GPU. If you see that your GPU is not working or maximizing, both ends aren't good. If it's not working and you're running deep learning, that means you're using CPU, stop, because you might not work well with your machine, especially if you're doing an imagery workflow. And if it's overutilizing, you might want to get your batch size a little bit lower. Remember, we talked about batch size. So this is a good indicator. Usually you want to utilize 80% of this to run through a deep learning workflow. Now, something to mention since we're here, there's certain versions of the software that actually now supports multiple GPUs. So if you're working on a size of a country, you might have a beefy machine with multiple GPUs on the cloud. You might have 2-4 GPUs out there, and that will have 4 different entries rather than only one here. The software will utilize all of these. It will parallel process and get the job much faster. So knowing the hardware is very crucial. Any other questions coming from your side or Rohini's as I move forward?
No, very good. Thank you.
Thanks. And Lisa, really thank you for showing us how to go through a very simple workflow, utilizing in this use case 1 meter imagery to get something. And it's not, as we said, you really showed that it's not about GeoAI, it's about the use case. There's damaged houses. We want to create a data set which we can build on, providing that data set through a field collection application that you can go and ground truth the data, connect with the locals, will complete the story of AI because it works together rather than one separate workflow. So with that, I want to really just reiterate what we've seen. We've focused mainly on the imagery workflows up till now. We've seen out-of-the-box models and detecting informal settlements. Think of any use case where there's camps, informal settlements, that might be a good workflow to follow. We've checked on flood detection a little bit, and I showed you something with Sentinel imagery. So keep in mind that you can work with different imagery and you can extract any of the features out there with either trained models or models that you train yourself or do reinforcement learning on. So the floor is pretty wide for different experiments and different workflows, and keeping these in mind will help you move forward. Now I'm going to shift gears a little bit and I'm going to get away from imagery deep learning workflows and jump to machine learning a little bit, because there's also a lot of use cases where we're going to apply machine learning, where we're going to use different regression models, random tree models, different statistical models to predict something. Usually, data sets in nature, well, features in nature don't occur alone. They're directly and indirectly related to different factors. Let's take this use case, for instance, where we're looking at above ground biomass prediction, and we're going to see a detail of the workflow. When we think of above ground biomass, well, it's how much the tree can trap. And that is dictated by a lot of factors. Soil type might affect that. So vegetation cover might affect that. The type of the tree, the sun, look at the sun direction, the elevation we're working with. So there's a multiple layers that can affect such prediction. And hence we're automatically thinking of a regression workflow, somewhere where we can predict based on different layers. Now for that, what we wanna aim for is predicting above biomass ground on the scale of Cantabria in this use case. And we want to do that through publicly available GEDI data, which is global Earth data from NASA. That is the easiest way to tell the story. It's LiDAR data from space. Shoots a point, captures something on the trajectory of the station, and that captured data or LiDAR point got different attributes in it. One of these attributes is estimate measurements of above ground biomass. Now, the challenge is if I look at the screen capture down, this is not continuous data sets, and I'd like to make it continuous data set. Let's see how to utilize that with available out-of-the-box software. So I'm going to jump again to my Chrome, where we were here, and let's see this guy here. So the story of above ground biomass. Our aim is to predict above ground biomass on this scale. And this is actually a prediction. It looks complete, nice, and I can see that there's on a high level, we'll get to the details, more above ground classified here, the darker color compared to the lighter color. And that really follows the forest cover actually. You can look at this and there's the high values and low values. Now, how did we get into this? Let's go through that story. We've got the GEDI data, which I just explained. We've got Sentinel imagery because we can drive a lot of different indices that will help us estimate a GEDI or above ground biomass, and a DEM, as I mentioned, the elevation, the slope affect what trees grows, how do they grow, which will affect our prediction. Now, when we get that data in, remember from our earlier story, data prep and data labeling and data cleaning. We had to do some data cleaning found with different algorithms that are available to clean clouds from Sentinel-2 imagery, created a clean image where we had data between May and September for 3 consecutive years between 2020 and 2023. cleaned all the clouds and took that representative data sets. Now, to get a more accurate model, I would start with, I might want to include more time slots in that. So these just small details on these parameters and how they we got this image, cleaned it, and then we extracted a couple of indices. We're going to explore these indices that we used on top of the GEnAI data to train a regression model and predict above ground biomass. Our raw data, as I mentioned, it's from space station, it's trajectories. You can see the trajectory of the space station. We clipped Cantabria, and then we can see each point in here. So each point of these will have a measurement, and we're looking for that estimate of above ground biomass data. Now, note that the GEnAI data comes with 6 or 7 attributes. I don't have that in the back of my mind. One of them is the above ground biomass. Another is canopy height. There's multiple more. And the same workflow can be applied to these layers or any similar workflow with complete different inputs that applies a regression workflow. These are the data that we used. We imported that data. And as I said, I picked above ground biomass density, canopy height is there, and these are the other attributes actually. And this is also an available public story map, which will be shared at the end in the one QR code that will give it all. So if you're keeping track of that. We imported the data, and then we wanted to get the imagery, as I mentioned. So we got the Sentinel imagery, and you're looking at a cloud raster function of the raster or the Sentinel imagery with no clouds. You can see there is no clouds out there. It's all been cleaned, and it's ready for us to use. These are all the bands that are available within the set of imagery. Now, once we get that imagery, we, as I mentioned, clean the clouds from it, utilizing different raster functions in this use case to remap and use the QA band that is available within Sentinel. Then we also get a digital elevation model, which is available. There's 30-meter available digital elevation models, 10 meters. In this use case, it's a 5-meter available by Cantabria, also publicly available. So depending on the location, you can find different DMs out there. After getting that in, we started producing our derivatives from the raw data. So we got our imagery, and we started extracting different bands. The first is the NDVI imagery, which we used NDVI raster function to get NDVI estimate. We then got the soil adjusted vegetation index, and there's formulas for all of these. As you can see, they're here. You can just pick them up or use them or hard code them or pick them dynamically from the image. There's a lot of potential in here on how to apply this. Then we've done the modified normalized difference water index, and I'm not gonna go into all of the details of each one of them, but just to get an idea of how much we can drive, and all of these affect growth of trees technically. So moisture stress index is another derivative, ratio vegetation index, and there's a legend that explains each one of them, going to the DVI. So that gave us an idea of all the different layers that we've extracted from our raw clean Sentinel imagery, cloud clean Sentinel imagery. We then got the DM. You can see our elevations here. From the DM, we've driven the slope. Certainly, these are very high slopes, so we don't expect any trees to be growing here, for instance. Aspect, sun direction, how the slope is looking. And then once we got these, we imported our imagery, our indices, our other indices from the DM, the target value feed, and our point GEnAI data. Trained a model and got an R2 value of 0.77, which is relatively high for the small number of bands that we've used, or the small numbers of trajectories. So we imported 3 trajectories out of 7. As we import more data in that use case, the model should perform much better. Now, keep in mind something that I might have skipped and I want to mention in here is, as I train on the data, I mentioned that we had to first clip the data, import it, and that was data prep. Then there was the data cleaning. Some of these GEnAI measurements are 0 due to clouds, due to malfunction, due to anything, or some of them are with no values. We want to remove this from our training data, because if we train on it, we're technically not training on real values. And we actually did that here, which helped us get a better accuracy. Once that was done, we were able to predict using the prediction tools in the GIS system, and we were able to predict the above ground biomass In this use case that's up in this guy here, we're looking at Sentinel imagery on the left-hand side, and we actually applied the same workflow on Landsat imagery, which is this side. And the first thing you should be able to stop is the resolution of the data. We're looking in here, this is much finer, as this is 10 meters, sorry, compared to the 30-meter Sentinel. And the first ground truth that I can look at is if I overlay this with my imagery, you notice the darker areas are over my forests, which are telling me that the model is going the right way compared to here, which is less. So the predictions that I got for above ground biomass are pretty accurate in here, and I can look and pick up pixel values, and this is the 151 AGB measurement on the Sentinel imagery, for instance. So with that, we've seen the workflow of prediction, of ML prediction with ArcGIS. There's a lot of other use cases that we can explore, and we'll share also some of them, but it's always good to look at the different ML workflows out there and how can I be of help. I stayed on this screen for a moment in case you want to access the story map. This is publicly available. You only have to scan this code and you'll get there. Let's see. Another very hot topic, and I'd like to have this as the last part of the workshop, or the last topic, since we've covered a little bit of deep learning, a little bit of ML, and let's cover a little bit of GenAI. And GenAI is another hot topic that is coming on. It's mainly utilizing LLMs in the backend to help us through different tasks. These tasks can be heavy tasks, tedious tasks, stuff that we're gonna extract things from different inputs, utilizing the text prompting and working with different variety of models to accommodate that. Our use case for today is really integrating LLM OpenAI with a workflow that WMO is working on. So WMO originally, and let's put the story in here, is capturing extreme events data, which you can publicly find available if you Google the climate report action from WMO. I can actually pull that one out. Climate, state of global climate. Let's pull the 2022. There's a 2023 already out, and 2024 is coming soon. And the state of global climate is really following climate events between atmosphere, land, ocean, and different categories all over the planet. There's around 80 different meteorological organizations that report extreme events globally, and they'd like to get a global figure on how's our climate doing. Now, for that, WMO is capturing a lot of data, and within this data, there's a layer that got attachments, where if anyone or any user gets to submit an extreme event, these users, as I mentioned, are the governments. I'm going to clear this guy, and I'm going to explain this in a moment. But what I'd like to do is get to this data set to really show you how does it look like. So let's see. I want to copy the ID. That would be the easiest way to find it. And oh, maybe I need to sign in, and I'll share it publicly, as that can be a publicly available layer. Sorry for this. I'll share at the end the public. So this is more the internal one just for my testing, but the data is available public if anyone wants to access it. So I'm going to the layer, and just to get an idea of how things look like, there's extreme events reported on different admin boundaries. So we've got the admin boundaries. There's 290 admin boundaries up there, admin 0, so countries. And each one of these might have one or multiple extreme events reported to it. The data looks very structured, and it's being highly utilized on different events that are being reported from around the globe. We're looking at New Zealand, for instance, flood event, etc. So there's plenty of different information in here that we're not going to dive into here. What we're interested in, and we're going to get to the story of GenAI utilizing photos and files. So I'd like to find just one of them where I can look into the photos and file, and I can see that there's a document in here. And this document will have, that's a good example. I'm not sure which language is it in. I need to go back to the record, but it's great. It's something that you'll have multiple attachments. I can tell you we've seen a PDF. We'll have multiple types. There might be JPEGs, there might be Excels, CSVs, and they might come in all these different languages. So they'd like to know what is in here. And I think this is Sweden. So what is happening in the data or in the attachment, and if there's any missing information that they can capture to the extreme effect. Now, to do so, I'm going to jump to my demonstration in here, and for that, I'm going to be showing Python. So for the developers in the room, this should be understandable. For those who are not, I'll try my best to go through the workflow. In any workflow, we usually need to import libraries. Sometimes you import the libraries from the backend or from the interface as we do, and sometimes you can just hard code them in a tool that you recreate. So I'll import libraries. I'll be using multiple libraries from multiple sources in here. As the data set you just seen, so this one is not publicly available. The one from WMO is, just because I'm adding this into a more of the demonstration. I'll get this data in, and what I'm interested in is grabbing all the attachments of the data. So I define an attachments area, and I've defined an attachments directory, and I want to create this and work with it. The next step is I want to get all of these attachments. Note that we have 500 extreme events, as I looked at back here, 576 different extreme events. So I'm not going to stay the whole time processing these. I'm just going to pick a random number between 100 and 110. So the 101 till 111, since Python indexes as 0. I'm just picking these 10 features, and hopefully there's an attachment in one of these 10 features. I'm going to run through that, get each feature out, go if in its attachments. Sometimes it might have one or multiple attachments. We've seen one with one, and just go and download this locally with the download attachment functions, which is happening here. So accessing feature layer, specific object ID, and attachment. And great, this is actually a good example that I'm running in here. So I'm downloading different attachments. There's a PNG downloaded. You can see that there's another PNG downloaded. We're hoping for a PDF. Hopefully we'll have one PDF that will let us go. I can see also that there's coming different languages, so it's not going to be English alone. There's JPEGs coming, more JPEGs. I'm looking for one PDF. Hopefully we'll have that. If not, we'll just stick with the JPEG example. In the meantime, I'm going to launch my Azure Chat OpenAI model, which is using GPT-4 in the backend. So it connects to the AI model out there. It's still downloading, so this is going to take a moment to download and then run this guy. Once it's provoked, this is even interesting. It says that I'm ready and available AI token is ready for you. The next step I want to do is really extract this data. And for that, I've created two different workflows, one that extracts a PDF and one that extracts an image. That's something I'd like to do because I didn't see, I told you I'm running on unknown here for the sake of the demo. There might be another PDF. So I'm just going to download a little bit extra data as this is going. And I changed the inputs here. If we look into our examples, attachments, yeah, there was no PDF, so it was safe to run something on a PDF. This is initialized. Now we've got a PDF. That's good. So at least we have something to go with. We initialized our LLM model, and I'm designed it to work with images and PDFs. Now we can add more. This is just to show you what we can do with it. We can add Excels, we can add CSVs, Word, etc. What we're going to do is process each one of these global IDs to relate it back to the original feature. because each feature got a relationship based on its parent global ID. So we're maintaining that in the naming, and the code is designed for that. It's gonna go through it, open the attachments, and use the extract from image function, which we've pre-cooked, and the extract from PDF function. So it's going to launch the image extraction chain and the PDF extraction chain. Now, what am I talking about? Let's look into the PDF extractor. And this is a pre-class that we've written where it does one major or a couple of major things. It extracts text from PDF, so it uses the OpenFits library to get the PDF out, transforms it into text, and then it invokes a self message that tells the model return JSON information, only return JSON format. I don't want you to return text and what you think, and do not provide any other commentary. So I'm specifying that the model returns JSON data. And this is very critical because JSON is structured. So that's the first step. I got unstructured data and I made it structured. What I'm also telling it is use PDF information, which is something we call based on pedantics libraries. And what this means is you can define what the model would return in a JSON format. I would like it to return a title, an author, number of pages, number of graphs that are in there, and a bunch more. Now, it wouldn't alone know that the author is author. I defined it that it's a string, and the description is author of the PDF. That's what the text prompt that the model will take. For the number of pages, that's this. So you define what you want in there, and you can import strings. You can get integers. So I want number of pages as an integer in this use case. You can also return lists, which is lists of keywords associated with the PDF document. Read the document and tell me what different keywords you find that might relate to the document. I want a summary of the document, and I want main topics discussed in the document as a list. So defining these will really help us get more curated results. The next step was also to do the same with image. So if you see it's slightly different in a workflow, in a production workflow, I want to make sure that image information and PDF information got the same structure. Again, this is for showing capabilities. So we managed to change a little bit. I'm asking it to pick any measurements. If you find measurements in there, point measurements, location point measurements, and average measurements in there. And for instance, point measurements are list of numbers of measurements in the map, if there's a map. Explanation of why did you pick these measurements, just to really go and double check that. So with this understanding, let's run this code, which is, I believe this is done. Yep, it downloaded some, and we have one PDF, which is great. At least we'll get one example out there. It's now going through all of these, which is quite a bit. But think if any one of us want to open each document and read through them, assuming you know the 80 different languages that may, well, 80, some of them are English and Spanish. Let's assume we have 20 languages at least in these different documents. You will first need that capability, and second, the time to open each one of these. Now, how it looks like, that's an idea. That's what we actually looked at on the extreme reported events, so the Swedish data. And let's see what this will look like. So it will go through each one of these. It will analyze either the image or the PDF based on what we just seen. It will then return the feature attribute. And what it will do first is it will actually dump a description to our label, or to our feature. That's why I have a copy, because we're not adding the AI review directly to a public data set. We're just, for the sake of the demo, adding it to a local data set. So you can copy the data, add an AI reviewer, and add attachment description for this use case, which is just extract the attachment description from that attachment. Then it's going to add the feature and push that forward. As you see, it's been running for 1 minute, 26 seconds, and I think it's going to go for 1 minute extra. It's doing that and pushing reviews to each attachment based on the global ID that I mentioned out here. So to verify that, let's look in here, and actually this is automatically updated. So you see that the AI added a review for this data set that is titled, I can't read Swedish in this use case, but we can also ask it to translate the title if it's there. But then it adds, it's a 24-page document created and modified September 22nd. It's in Norway. Sorry, I missed Sweden for the map. Why did I say Sweden? It's Norway. And that's a good correction for myself, actually. It's discussing extreme conditions in some regions. There's some keywords out there, and again, listing some information. And it's not the only one out there. It's doing that for a bunch of the features. You can see the image titled hailstones in hand shows a close-up of a hand holding two large hailstones. In this use case, large ice, and that's reported. So we're able to pick up this up, or dried cornfield in this use case. So you might get all of these different options, and it will automatically push the review to the data without any human intervention at this use case. Now, is this what you want? Maybe yes, maybe no. I would also add a reviewer field. If it's approved and read by someone Q8, Q-Seed, I'd push it publicly. If it's not, then I might want to revert, clean the data, work with the model a little bit more to get better results, then move forward. So it finished and it processed all of these. Now for the sake of understanding, so we've only seen the description, but I've already showed you in here a little bit more than description, which was in the information. So it got title, description, point measurement. Where are these? Well, these were appended to a data frame. We've got one for images, and you can see that's the first one. So hailstones on a bench, large hailstone in hand, and it gave a title for each JPEG or PNG. It gave a description. There was no point measurements in these, so it didn't give any, which is good, as they're just images. And well, let's move to this side. There's no average management. There's no country, as there was no maps. Some of these images might have a map, actually, and in case there's a map, it figures out what the country is. I think it will figure out the country in the PDF. And then main objects. It's giving what is in the image as main objects, which you can easily use as categories to filter and find data rather than just opening endless amount of documents. And most importantly, the global ID, which gives us an idea on which feature it came from and how can we relate it back to it. Now, the last bit in here is the PDF, and we've got 3 PDFs out there. That's the title of each. Oh, I had my understanding machine learning PDF in there. Nice. That doesn't relate to the data. I might have just dropped it. It then got the number of pages in each. This is just a dump data that I have in, so sorry for that. It picked up the creation date of the PDF, the different keywords in the PDF, and then a summary and main topics. And again, everything is possible for experiments here. So the more you add to this, the more you experiment, the better you structure your prompt, the model will operate better. Keep in mind also, this is with the GPT-4, not with the latest one that came around 2 days ago. So once that instance is available, I believe even the model might give better data here. Hence, we always want to keep experimenting, exploring, and pushing these functionalities a little bit further. With that, I've been talking about this for a while, right? So it's time to scan this. If you don't have it, it's a good moment to do that. I'm gonna open the document in the meantime on another screen and just drag it to this screen. Stay with me for a second, sorry. That's the model back. And I'm getting the document locally myself to go through it. Yep, perfect. So this is a really detailed document on tons of resources that we've showed. We're starting with the deep learning model architectures. Remember, I showed you the metadata, the backbone model. This is a really handy resource out there that can show us this. I'm not going to click every one of them, but just to get to the all different pages that we've shared. The different extracting building footprints, the methods that you can use, some guides on getting started and installing deep learning, the change detection stories, some courses are available out there for us, some resources on segment anything model, TextSAM, some tips and tricks. This is actually also very handy resource where it goes through the needs. This is the question that Mike answered, understanding GPU, CUDA, what do we need in the back end, how do we understand what GPU do we have, and how do we access NVIDIA SMI. So everything is pretty well documented in there. I also like this one quite a bit because it goes over some main definitions. If you want to access the DLPK and understand the open source libraries behind PB files or H5 files that you can access, goes through how to get a DLPK, how to get an imagery and understand what is the imagery you're using. That's where it explains cell sizes, raster information, and certainly tile sizes and what do they mean and how should we tackle tile sizes. Always remember, no parameters should be taken for granted. So understanding a different tile size will result in different results, slightly different results. Not always, but I think this is a good example in here, this building and the building down. Then batch sizes, thresholds, etc., etc. So there's plenty of different parameters that we should keep in mind. Then some other resources on deep learning packages, out of the box assistance, which we really didn't show, but that's due to time. We can spend a lot of time on these different topics. That's another thing that we'd like to go through. And finally, some videos to get more interactive learning out there. And with that, I aim to stop at this time 4:30 CET to take some questions and open for discussion since we might have some lined up. So thank you all, and thank you, Lisa, again for showing the very interesting yet devastating work in Grenada.
Wow. Thank you. Thank you so much, Rami and Lisa, as well as Mike. This is a great session, great presentations, and absolutely interesting demos. I've learned a lot. I found it quite educational, and I'm also quite inspired to see the potential GeoAI tools offer when it comes to humanitarian use cases. As someone who has spent over a decade in the humanitarian field trying to use GIS and Earth observations and tools to improve humanitarian responses, I'm both overexcited as well as I remain cautiously optimistic on our ability to operationalize many of these tools. Right? So let me start with some questions. There are some great questions coming from our audience as well. First, you briefly mentioned this over your presentations. What are the biggest challenges in running these models, and what do people need to prepare even before starting on this? So maybe, Mike, if I could direct it to you, and then Rami and Lisa, if you also want to chip in later.
Well, I mean, Rami and Lisa are the experts. I would say that, the most important thing is deciding which of these foundation models that, are going to be most productive for us. And I think that's, for those of us who are not expert in this topic, that's the big question. And I suspect that in many cases, you follow the people ahead of you, right? So you're working in a particular field and people tend to use this model, so you try that. And then you start experimenting, with some alternatives. And, I'd like to know from Rami and Lisa, to what extent is the SAM and the SAM-based models, to what extent is that kind of taking over many of the others?
That's a great question, Mike, and a great answer, because I believe always and foremost, the most important part is first figuring out which model. That will dictate everything else. It's a chain reaction, technically. Model takes us to machine, takes us to training data, takes us to parameters, etc., etc. So as I decide which model I'm going to use, I'll move forward with that workflow. But then you really mentioned a great one, which is, shall we use SAMLoRA? Is it the good example to be used? I briefly mentioned that really depends on the use case. If you're not interested in high accurate footprint, as you're not taxing, for instance, if you're a tax authority, you really don't want to get 10 meters for someone extra and take their money. But if you're interested, if someone built a new house, for instance, and I just want to know it's there, to send my surveyors, or if there's damage, to send my aid in there, or if there's tents, to send my aid, then I'd use SAMLoRA. If I'm in a different use case, I'll explore a different model. Now, SAMLoRA is fast, and that's why I'd use it today for these use cases. But also Deep Lab is very fast, and we didn't show any Deep Lab workflow. Deep Lab is more efficient from our experiments when it comes, for instance, to detecting different plant species in the imagery. If you're working with that, maybe you want to experiment with Deep Lab. Now, is this the workflow I'm going to be working with? Not next year, next month? I can't answer this question. As we've started discussing, there's something new coming every other week, every other month. So models are only going to get better, and it's only going to grow. We've shown 75 models in the Living Atlas and around 20 backbone models or foundational models, plus 3 combinations of each at least. So that's 60 plus 70. We're around 150 models. We need to keep notes of what's happening and how can we utilize them and what's the best way. But also, I'd like to give the floor for Lisa for her personal experience in there, because she was actually working with training data and with the hurricane data. And I believe she faced some of the challenges to figure out what does training data look like. So maybe Lisa can tell us about why training data might affect how our models work like.
Yeah, I'm a scientist by background, and I'm sure there are a lot of scientists in the audience. But I think going through our literature review, seeing what other people are doing, even having conversations with our teammates and looking at what they're doing, helps you get started with what direction you'd want to take. And then as a scientist, I love to just experiment a lot with different, say, like I could make different training data sets and test out how the model runs with that, or use different models, and just having fun with it. Yeah.
That's great. Thanks, Ethan. Thanks, Rami. I fully agree with you. 150 models, like how can people keep track of it, or which one becomes more useful? It's a field that is evolving very, very rapidly. Let me jump into a couple of questions from our audience. Our HM Omrani has a question on damage detection specifically. Does it make sense that the performance with regards to classes 1 and 2 are relatively low in what we were seeing earlier? Do you have any quick update or input to it?
That's actually a good one. I think, knowing, because I worked with Lisa on this one and I've seen it, it's actually should be around 0.8 and 0.9. That's the different screen capture that was included in there. So maybe we referred to an earlier model that we trained. And this is actually great because it's something we learned as we were processing. The class 1 and class 2 were reported lower because we were including all the area with no data and not creating an AOI mask. And that thing that sounds so simple, just draw around this, well, it's very crucial. The next iteration, and I think I'll add that to the updated document once we send the PDF, you will see that actually it increased from low to around 80% due that we minimized our training samples by just including labeled data rather than unlabeled data that might have no data.
That makes sense. Thanks, Rami. Devika has a question. What are the possibilities for nonprofits to work with GeoAI solutions at affordable prices?
I will give that question for Michael, as he will certainly have way more information on it.
Well, I mean, there are lots of solutions. From the Esri perspective, we have special programs for nonprofits. We have special programs for the conservation community, special programs for the educational community. There's a whole series of sort of deep discounts and donations for certain types of projects. So I would say certainly contact your Esri representative if that's the route you're going, right? There are other alternatives, of course, right? And it's not to say that you can't do GeoAI with other software solutions. So I guess it'll depend. We always need to keep in mind that, in the end, it's not just the software cost, it's the cost of the entire project and its time and its people and its data and its expertise and that sort of thing. So I would say just reach out to us.
Thanks, Mike. That always helps, and absolutely. John Mattison has another question. Which models might you recommend to look at oceanic physiochemical parameters? So it's quite specific. And that also ties me back to one question I had for you, Rami. How important are these hyperparameters in the models if you want to combine both of those?
That's actually a very good and challenging question. I would be lying if I say I've worked on oceans workflows. Aside from water, well, I did flood, what we can see on the surface. Now, keeping in mind sentinel workflows, as we're seeing sub-layers, and it doesn't directly mean ocean, but at the end of the day, workflows are workflows, and we should follow a methodology. I believe if we're working with imagery data, our image might be one or multiple bands, and some features might show on certain bands and might not show on others. A non-ocean example, again, as I'm not specialist in the ocean field, is I find the Sentinel workflow where we detect agriculture areas is a very interesting one. The red band and the near infrared really helps you detect agriculture better. So selecting these bands and training on them will get the model to operate better. Now, if you have any workflow where you can put a combination of bands and see what you're looking for visually as a first check, if you see it visually, I'd go and test with either SAMLoRA or DeepLab, just for the sole reason of it's cheap. It takes a couple of minutes to an hour, 2 hours. If you got bad results, you're not going to lose a lot of time. And if you got good results, it's gonna so you might not get a complete picture. You might be doing a lot of false positive of something, but you see a lot of true positives, and that might be a sign. Maybe you need a little bit more training. Maybe you need to move forward. So I test with these two first. If they didn't work, I'm more than happy to connect at further points and just dive a little bit deeper per use case. Now that what takes us to the second question that Rahini got, which is use case and hyperparameters. It's really important thing to keep in mind. And this is, I think, the third time that I'm going to get the chance to talk about cell size. Cell size matters. If you're working with forestry detection, most probably, even if you have 50 centimeter imagery, you don't want to process a forest on 50 centimeter, because 50 centimeter will have, you'll have maximum 3 trees per chip where the model is looking at. So imagine you're going to divide your forest 3 trees by 3 trees. That will end us with endless labels and a very high computational challenge. Then I want to go maybe to 2.5 meters, which would put 20 trees in one picture rather than 5. So hyperparameters resolution is very important. Threshold. All deep learning models have thresholds. Do I want to run with 0.9 and I just want the very accurate ones? Or do I want to run with 0.6? And if I get false positives because the model is working, models, technically, I've seen that a lot, and this is a good use case. Models might predict a lot of false positives in water, but I love it when it predicts false positive over a water feature, because we have our water always as polygons. Let the false positive be out. I'll take a 60% accuracy. It looks very accurate out of the water features, but then I clip with my water feature, got rid of all the false positives in a post deep learning workflow, and got out with a simple model. So that's very important. Another, I think that would be my last on hyperparameters, because I can go for days on it. I'd keep in mind batch size. So with training data, you don't want to give a batch size of 8 when your GPU is 8 GB. You want to give a batch size of 4 or 2 when you train a model. Now, when you inference, it's funny that per GPU, per batch size result might differ. So if me and you got exactly the same data, me and you got exactly same image, same deep learning model, same product, same software, we installed it. The only difference is you have a 4 GB GPU and I have a 2 GB GPU. We might get different results. Or we both have 4 GB GPU and different models, one from 2021 and one from 2023. We might get different results. So tweaking, testing on small areas, seeing the results, are they good? Let's apply on bigger areas before spending resources on larger extents.
Rami, a follow-up question. Don't you think it's a good idea to be sharing your work as a Python notebook so then people can get access to not only the results, but also all your work?
Absolutely. So it's a hard job. It's not an easy job to keep updating notebooks and sharing stuff, but I'm going to drop into, at least let's focus on GeoAI for now. So I'm going to drop a link in the chat with the GitHub repo, and I have already 2 different tools out there on the repo that if you find certainly these tools are in production, these tools are tools that I've created and sharing with the community. So if you find any challenges in the tools, let me know, post on the repo. If there's any bugs we can fix, it's been tested on multiple use cases. But also within the same repo, you can go above the GeoAI folder and look into imagery notebooks or general purpose code or feature service management. Because for instance, the code to download attachments that I showed, which is very critical to access these attachments, is also publicly available there.
Just to clarify, I wasn't asking you, although thanks if you can do that. I was asking, do you think we as the community should be doing that more often in this, in the sense of open science?
Oh, absolutely. Absolutely. Anything that is, I think anything that is available, any story, even a simple blog post, not a code, will help us move forward. Because in a lot of places, you just mentioned a while ago, you do what your surrounding is doing. So if you see someone, a new idea or a new workflow, you're going to learn from it and go apply it. So I really highly enforce sharing. And hence I do share and I'd love to collaborate more.
Thank you. Thanks, Michael, for the additional questions as well. There's one other question from the audience. Oscar Bautista has tested GeoSAM, open source implementation of SAM, to segment buildings in remote areas and found challenges with model performance in settings where humanitarian action takes place. It's usually quite remote. He's wondering if there are AI segmentation models that are pre-trained on rural sparse settings and also on non-traditional constructions. I'm aware there were some projects that attempted to do that in certain areas, but are you aware of any large-scale training data that is available?
So as training data, not really, because the challenge with training data is always who owns the imagery. And you tend to see that even if you get imagery through open source as Max or humanitarian initiatives or Planet humanitarian initiatives, you don't usually share the imagery publicly. So I wouldn't find that, but what I know is there's deep learning models that are available for that. So for instance, the Building Footprint Africa, which we briefly showed with Halo, was easier to train in Afghanistan than a European or American model. So that's one part. The other part that I'd expand is, you mentioned GeoSAM. I'd also explore with SAMLoRA as a different workflow, because SAMLoRA, again, it works a little bit differently, as you can fine tune it, do reinforcement learning rather than use it out of the box, and it only takes a couple of training samples, as these are shorts.
Thanks, Rami. That's quite helpful. I'm cognizant of time, but there is one pressing question I have on my mind, and I'm sure many of our audiences probably have the same question. So as somebody who's proficient probably in geospatial science and many applications, but new to GeoAI solutions, how long would it take to get a productivity level? Like, how long do I need to invest if I want to successfully run a model? I know some use cases, it might not work right away, and I would have to go back and forth and redo them. What's your take on that, Rami?
I can certainly talk about this for a while, but I think that's a great one for Lisa, as Lisa lately went through the damage detection workflow and she explored with these tools. So Lisa, if you can tell us a little bit about your experience, how long did it take you? And then I'll come with different thoughts.
Yeah, I first started with some growing pains just learning how to do it, but once I learned how to do the workflow, I think it could be repeated in like 2 to 3 hours, including the processing time. So you could process, go get some tea or something, and then come back. But yeah, also just following step by step on what you need to do will save you some time from reiterating the process. And even cleaning up the data post-processing, working with polygons is pretty quick too. We can do a quick query to delete any unnecessary or false positives, as Rami mentioned. So yeah, I encourage everyone to try it if they can get their hands on some imagery that they're needing for their project.
And that's good that Lisa mentioned all of these different parts. So I think from that perspective, you're looking maybe at 2-3 weeks to get more familiar, up to a month, but one topic. as you have seen, there's multiple topics, multiple fields. I'm personally still learning as everyone else on GenAI. So there's no advanced, well, there's some advanced users for sure who are just focusing on GenAI, but it really takes a specialty. So I think it takes between 2 weeks to 3 months, depending on the user time, how much time you have, how busy you are, to get going with the tools, but not all of them. So figure out a topic. What are you going to work on? What is the most important one? Are you interested in image classification? Then start with that. Are you interested in regression models? Then start with that and build on that.
Yeah, I also wanted to mention, like, I particularly don't have a background in AI. My background's more in earth science. So I really want to encourage anyone, even if you don't have a background in AI, that you definitely can do it. Yeah, I just want to encourage people.
Thanks, Lisa. Thanks, Rami. That's quite helpful. As one last comment from our audience. So we have George Cummings from UNESCO Ocean Unit recognizing the value. They need to know the highest population and lowest sea level communities where they are at risk for tidal challenges. And just overall recognizing that GeoAI solution has this wide range of use cases, which I fully agree. Now, Rami, Lisa, Michael, all of you, thank you so much for taking the time to talk to us today and doing this webinar. It was very informative, and I'm sure all of our audience found it the same way. And thanks to also all our colleagues who made this event possible, and our engaged audience for their active participation. This presentation is available in the neural network, so you can download it, and you can also watch the recording on YouTube and our neural network. And I would also like to take a very quick moment to remind that we are currently running 5 competitions as part of the 2024 GeoAI Challenge at the AI for Good. You can check the link in the chat now. So GeoAI challenges, just a quick introduction, they are competitions aimed at providing solutions for addressing real-world geospatial problems. And it aims, obviously, to use AI solutions, mainly machine learning techniques. And our participants get hands-on experience in using AI solutions in areas that are completely relevant to UN Sustainable Development Goals. And there are prizes, recognitions, certificates. We do have 2 competitions that is ending in 2 weeks. So one is on vegetation mapping and a human settlement detection. Both are by the Mexican National Institute of Statistics and Geography. So if you are interested, please do hurry up and apply. The winners will be announced at the next UNGJM high-level forum in Mexico City by October. We also have 3 other competitions, just in case if those are the use cases that you really like. We have one curated by Politecnico di Milano and University of Padua. It's on the ground level NO2 estimation, quite an interesting topic. There is another one, which is my most favorite, is on Amazon Basin Secret Runway Detection Challenge, and it's curated by the UN Office on Drugs and Crime. There is also the agricultural plastic cover mapping with satellite data by FAO. All of these are quite interesting challenges, real-world problems. They close around mid-November, so you still have some time if you would like to participate. And once again, I thank you all for your participation today. And with this, let me give it back to Anna.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
you.